I've handed back also the lab reports. I think for the most part, people did a good job communicating the equations that are in the spreadsheet. That'll become increasingly important as our calculations get more sophisticated with like the jet impact lab and the hydraulic jump lab and so on. So please continue that good habit of explaining how each column was calculated so I can understand what you've done in the lab. The flow visualization lab is due on Tuesday, and I already did the calculations for that lab. After the experiment on Tuesday, I sat down and took a couple of minutes to calculate the Reynolds number, and they're not perfect, but they're not horrible. You know, it's okay. You know, if I took the average for all 4 runs, because there's, you know, we defined what should be 4,000, the transition point between turbulent flow and transitional flow. Both groups did it twice, and so there's 4 total guesses of what that break point is, and I think if I remember correctly, the average of those is a little bit less than 4,000. And we thought we were seeing the beginning stages of turbulent flow much earlier than 2,000. The average of the 4 points was below 2,000. And I think that may be partly due to the fact that, you know, that needle is an obstruction to flow, and so it might have been causing turbulence that otherwise wouldn't be there if that needle wasn't in the way disturbing what otherwise would be a calm flow. And then also you have to think about the droplets of the streak, the dye that we were injecting. That liquid is entering the flow at a different velocity than the flow itself, and so it's going into the flow either faster or slower than the surrounding fluid, and so that's going to induce a little bit of turbulence too. So it makes sense to me that we saw what we thought was the beginning stages of turbulence before the Reynolds number was up to 2,000, because there were some other forces there that might have been inducing disturbances. So it was nice to do those calculations. The report that you need to provide is due on Tuesday in lab. Looks like I've got all the homework assignments here for homework 4A. Homework 4B is a short assignment, and that's not because that's really hard or anything. It's just that I used to group 2 assignments together, and I've split it so that there's less time between submission, and it's just smaller chunks. And so that'll be due a week from today, homework 4B. And that all has to do with rotational flow that actually we may touch on just very briefly today, but we'll cover in detail on Tuesday. So that assignment will be due on Thursday. Any questions related to announcements, grades, lab reports, anything at all, taking the big picture for the course? I'll just mention one other thing, is I'm going to be emailing a survey link to you today. And as you know, Marshall has an evaluation system where at the end of the semester you take a course evaluation and give your feedback on a course. But I've created a survey that I administer just informally because I'd like to have your feedback before it's too late. Now really, if you think about it, getting the students' comments at the end of the semester is a lost opportunity, because if you have concerns, then there's nothing I can do about it because we're all done. So I'd like to have your suggestions and your ideas about how the course is going now, so I can, you know, make improvements if they're needed, or if there are things you do like, I can maybe expand on that. I'll be emailing you a link to that immediately after class, and of course it's anonymous, and so I have no way of knowing if you did it or not, but you know, you have an incentive to participate and have your opinions known, just because I'll try and make adjustments where possible in response to your feedback. So look for the link that I'll email you that immediately after class. It's a very short survey. It shouldn't take you any more than a couple of minutes. Okay, Euler's equation. Euler's equation addresses issues like what we just saw with a pipe, flow accelerating in a pipe, or Euler's equation addresses local acceleration where we have some sort of a box that may be accelerating to the side and also accelerating down, and we've got a couple of locations. We want to know what's the pressure difference. Remember, Euler's equation answers the question, what is the pressure? And another thing that Euler's equation can address is how a liquid level responds to acceleration, because either the pressure is going to change or the elevation of a fluid is going to change when it's accelerating. And the first clue of that is built into Euler's equation itself. Here's piezometric pressure in the brackets. That's the expression in the brackets. Earlier in the semester, we defined P sub z as the pressure plus gamma z, where if we have some tank of water and we've got a vertical datum where we're measuring elevation from, then in static conditions, the piezometric pressure would be constant, because as we're going down through the fluid, maybe the pressure is increasing, but as we go down through the fluid, we'd be losing z. And so in the static condition, the piezometric pressure is constant. But remember, Euler's equation is used for non-static conditions, when the fluid has motion and it's accelerating, local acceleration. So if you had an open pan of water and you started accelerating it to the side, then the surface of that water is going to respond to the acceleration. And if you think about a glass of water that is full to the very top, the way that you don't spill that water is by moving slowly. And the reason you're moving slowly is because you don't want to accelerate. Because when you do accelerate, the water surface changes. Think about, here's a tank of water that's just motionless. And then as it's accelerating to the right, the water surface tilts. You know, you can think that if you accelerated too much to the right, then the water's going to spill out of the side there. And that's what's being represented here. It's a little bit challenging to interpret that figure because it's showing both cases simultaneously. That's why I've broken it down into the before and the during acceleration. So in this figure, what they're saying is there's acceleration in the x direction, sideways. And there is this new surface, A prime, B prime, that sets up during the acceleration in response to it. And the question is, how tilted is it? And we can use Euler's equation to answer that question. As we accelerate the tank to the rightward, the fluid level increases on the left side. So here, when we apply Euler's equation, we're going to have a location 1, we're going to have a location 2. But instead of just answering how is the pressure different between those 2 points, Euler's equation can also answer how is the elevation different. So instead of solving for P, we can solve for Z. Along the bottom of the tank, the pressure is going to be changing as well. Think about during acceleration. So in the case where we have a tank of water that's being accelerated to the right, so the water level is no longer flat. Now the water level is like this as it's accelerating to the right. Vertically speaking, there's no out of the ordinary acceleration. There's just gravitational conditions vertically. So the hydrostatic equation still applies in the vertical plane. And so here at the bottom of the tank, there's less water above it than over here. And so along the bottom of the tank, the pressure is going to be increasing in the opposite direction of the acceleration, simply because of the water level increased in the opposite direction of acceleration. We can know what the angle is that is formed between the horizontal and the new liquid surface. That new angle alpha is simply the tangent of alpha is the acceleration in the x direction divided by g. And it makes sense. If you think about if you were accelerating to the right at the acceleration rate of g, so if we had the acceleration is equal to 9.81 meters per second squared, what that means is it's being accelerated to the right as much as gravity is accelerating it. So it was horizontal. The reason why it was flat was because of gravity. So if we're accelerating sideways as much as we are experiencing acceleration due to gravity, then it's going to be a 45-degree angle. And so what is alpha? Solve for alpha. If we have 9.81 divided by 9.81, so tangent of alpha So what is alpha when the tangent of alpha is 1? I think that should be that the angle is going to be 45 degrees. We're going to do things a little bit differently today. I'd like you to work together in groups of 3. Let me see how many students we've got today. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we're going to have one group of 2. Everybody else has to work in groups of 3. And we're going to do an in-class exercise where just trying to get to the heart of Eulers. You know, this mid-semester feedback that we do, a couple of years back, it became clear that students needed a little bit more time working with Euler's equation. And so we're going to do an in-class example that utilizes Euler's equation in 2 different ways. One is just an extension of the tank moving problem that you've already done. You did a tank moving problem and submitted it today. But the tank moving problem that you submitted, it was find the unknown pressure. This first problem changes it around a little bit, and it says if the pressure is known, what is the distance between 2 points? So it should be pretty straightforward. The second problem is this one. You've got a tanker truck driving down the road, and it will never accelerate or decelerate more than 8.02 feet per second squared. Now, you can see we're in traditional units here. G in traditional units is 32.2 feet per second squared, and so it's not going to get to a 45-degree angle because it's never going to accelerate or decelerate as much as G, but it's going to have some angle to it as it's slowing down and speeding up, and we want to find out how deeply could you fill this without it spilling. You know, if it was full to the top, if it was all the way to 7 feet, then it couldn't accelerate at all. But the lower that liquid level is, then the more it's going to be able to accelerate and decelerate without any splashing. It's not going to go over the edge. So think about, we've got a truck with the lights on, which is important because that affects the acceleration, I suppose. The lights are on so the driver feels comfortable accelerating and decelerating more. Alpha describes the angle between the horizontal and this inclined plane that sets up during acceleration. So in this case, is the truck accelerating or decelerating? It's accelerating to the right. Exactly. So if it's moving to the right, it's accelerating because we got the liquid all the way to the edge. And the question is how deep can it be filled without spilling? So it's a little bit of a geometry problem, a little bit of Euler's equation problem. So let me give you, everyone will have their own copy of this, but I'll just ask for one of them to be submitted at the end of the class period. And the point isn't to solve the problem so much as it is to understand Euler's equation. So really, the main thing I'd like you to focus on is making sure everyone in your group gets it. And make sure that everyone is forced to do the calculations. Don't have one person being quiet and not engaged. So we'll spend, I think we've got about 20 minutes that we can spend, maybe 25 minutes that we can spend on this in-class exercise. And then we'll start talking about the beginning concepts related to rotational flow at about noon. All right, so get into your groups of 3, and there can be one group of 2. Okay, so with the in-class exercise, we saw the response of elevation and pressure changing because of local acceleration in the case of the Euler's equation. Was there other groups I can collect from? Thank you. All right. Thanks, Robbie. Whose am I going to take? Oh, yeah, and make sure that everybody's name is on it. All right. Thanks. Anybody else? Okay. It goes as an assignment. No. They're not quizzes. A quiz is sort of the deer in the headlight points. This is the comfortable environment points. Those are 2 different buckets. All right. All right. Another thing that can cause changes in elevation or pressure is centripetal acceleration, not just the local acceleration that we've been talking about. What I mean by centripetal acceleration is the kind of acceleration that causes rotational flow or a vortex. And so it may be water draining out of a bathtub, or it can be air flowing in circular motion during a tornado. And here's a video that illustrates a water vortex. At the beginning. This is these slides are today. Velocity, tangential velocity. So if you're measuring the velocity that is traced by the end of some particle that's rotating. So you have the end of the string and spinning it in a circle. Tangential velocity is the velocity around some circle divided by the circumference of it. And so the change in distance with respect to time, that's the tangential velocity, squared divided by the radius gives you the radial acceleration. Another way to characterize the velocity rather than the distance that's being the distance that's being covered by the particle is how many radians per second it's passing through, so the angular velocity. And so if you know the angular velocity squared divided by, multiplied by the radius, that'll also give you the radial acceleration. One last thing I want to show you is how to convert between RPM and radians per second, because in the types of problems we're going to do in class on Tuesday, that's a conversion you need to be comfortable in making. A lot of times machines and pumps are rated in terms of RPM, which means revolutions per minute. It doesn't mean radians per minute. Revolutions per minute. For example, if you had something that is 100 RPM, that means that some particle is going through 100 revolutions per minute. So that means 100 revolution per minute. The way that you convert that into radians per second is, of course, we know that there are 2 pi radians per 1 revolution. So if you go through 360 degrees of angle, then that's 2 pi radians. And then multiply that by 1 minute has 60 seconds. So anytime you have a certain number of revolutions per minute, if you need it in radians per second, and you will for these centripetal acceleration problems, the way to convert between them is multiply by 2 pi and then divide by 60. And so that works out to 10.47 radians per second. We've got the minutes canceled out. We've got the revolutions canceled out, so radians per second. So that's the conversion between RPM and radians per second. Okay. So that's just laying the groundwork for the rotational flow. For now, you could get an early start on the homework assignment. It's due a week from today. You know, if you read ahead in the book, you probably won't be able to solve the problems based on what we've discussed so far, but you know, it's all there in the book. But rather, what you do have due on Tuesday is the lab report. And so we'll work some example problems having to do with centripetal acceleration in class on Tuesday. Remember, I'm going to send you a copy of a mid-semester survey I'd like you to complete, and so look for that in your email within the next few minutes.